So hello everybody and welcome to another video. Today we will talk about regression, and this talk basically was given for the machine learning for the discipline series at AUB that I host, and we have basically here we're in the third session. So it is basically a recap of the third session, which was presented on the 27th of April. We will go quickly over to, as a reminder, to the classification problem. So what have we learned in the classification problem? We have some features, we have a model, and we have several classes in that we want to have basically at the end. So we basically train the model by known classes, known features, and we basically adapt these model parameters so that this model F, basically for a given set of features, for a given set of new features that it has not seen yet, put basically the right classes out. So the question, this is the typical cats and dogs problem. We show the model either a cat or a dog, and we then get classes out for cats and dogs, and by training it with thousands of images we then can show it the 1001st image, and we get basically out, is this 1001st image a cat or a dog? Okay. Right now the regression problem looks very similar, but has a fundamental difference, as you can see. We have features, we have again our model, but we have basically values on the output side. So basically what happens here is I have a set of features. I know this feature is basically defined by a set of values, and then we train, basically showing the model the features and the values on the other side. Okay. What does this look like? So let's imagine, for instance, okay, for the typical example that is normally given is housing price. So the feature might be how many rooms does this house has, what is the surface of this house, and basically then you get out, for instance, the price of this house. Okay. If you change one of these parameters, you get a perfectly out a different parameter. So this is kind of not boxes or something like this. These are like how should I say it? These are like values that can change smoothly. So if I change the value here, so the values here will change. Okay, so this is a different description of my object that I want to predict from the features that I show off. Okay, so we have this model, we have these basically feature parameters that go in there, we have model parameters that we tune in order to get the right target values, we can call this here out. Okay, very easy, not very complicated from here. This is a very general overview of the regression problem. Let's go into a two-dimensional case. For instance, I don't know, as I said, okay, I have a boat, and the size of the boat shall determine its price, and then I sample some boats and I get some price out, and basically then this would have only one feature and one value, typical two-dimensional case. So here, let's say here's the size of the boat, here's the price of the boat, and then you might get something like this. Okay, so small boats are here, I don't know, and the price is basically on this side, something like this. And you get a solution for this in the linear regression case, and then you can basically predict for this size here gives this price. Okay, easy as that. That's the linear case. What would be in this case the model parameters if this curve here is determined with typical straight curve y equals ax plus b, then this omega here would comprise the values a and b, and you could adapt a and b so that basically it gives the best predictable value for the feature that you show it with. Okay, this is basically it. That's easy, as easy as that. This is the simplest case of a regression. Of course, as I show you to you here, this doesn't have to be two-dimensional, so you can have a lot of features, you can have a lot of output. This is the typical regression problem, okay? Okay, a bit more generalized, this doesn't have to be linear, you can have a model which is some kind of curves that you want to fit, and basically then fit the curve into your points. This, as I said, this doesn't have to be two-dimensional as shown here for simplicity. This can be in here, like in this graph here, in 5 dimensions, even hundreds dimensions, thousands of dimensions, and then you get values basically out that kind of describe your problem. So the story is like, of course, you train again, so you train with data points in order to build this model, and then in the end, your model should, for a new data point, basically predict the right output values. Okay? As I said, housing price prediction, something like this is typically regression problems. Okay. Okay, so far and good. How do you train this? So how do you get basically your f? How do you find the right omegas for this f? And again, just as with the classification case, we have a loss function. Yeah. Okay, so what does this loss function look like? So basically, we have this L. Again, we sum basically of the distances. So how far are we away from the predictions? How far is the prediction away from the value that I know? Okay, so basically, as I said, you have to train this. This is a supervised learning step. So basically, you show some data to the system for which you know, for instance, housing price. You show basically some house properties and then the price to the system, so that for a new house you can predict the price. Okay, as easy as that. So we have this distance function here, which tells us how far am I away, and I want to basically to minimize this distance from the prediction error. Okay, so this basically gives me the prediction error, and I want to minimize this prediction error. And there are many ways how this could look like. So, for instance, if you imagine our linear solution here, we can just say, okay, this is the sum of the lines, which would be the distance from the prediction here, something like this, yeah. So the how far basically the points into which I fit my curve are away from the points. Okay. This can be done in several different ways. This can be done, for instance, in the Euclidean norm. Then this would be a typical chi-square fit, if you heard about this. And otherwise, this can also be, for instance, least absolute values. So just basically taking the real distance that you can measure from here to here between all the objects, and then you can still fit this curve, and this, for instance, in this L1 system, so L1 means basically the absolute values between the points and the curve, you would be more outlier resistant than in the L2 case, which is the Euclidean norm. Okay, so far so good, enough talk here. We want to continue in our course, and how do we minimize this loss function? Well, we adapted these model parameters. Of course, if you fit the curve A and B, for the linear case, for different cases, this can be, of course, way more complicated. But basically, you have model parameters that you adapt in order to make your regression problem happen. Okay. And you minimize basically this L by adapting these omega values. Okay, so far so good. We want to also talk a bit about overfitting and regularization. What does overfitting mean? Overfitting basically means, okay, we fit to some kind of data, but then when you go basically from your training set to the test set, or you show the system data that it doesn't know about, well, sometimes basically it works perfect for the data that you train on, but not for the new data, and this is basically a typical overfitting artifact. So your data predicts too well for the data that you show it, but it doesn't generalize on the whole system. So sometimes it's just better not to train too much, not to train too accurate, because then the model basically generalizes in a better way. Okay, this is the whole story behind this. We also have this regularization. So regularization is something that you can do in order to avoid overfitting. We will talk a bit here what you can do in order to regularize. There are several different ways. Not all ways are shown here. We will come back to regularization when we talk about neural networks probably. But here, what I want to show you basically is something that you can do, especially in this regression case, especially also in the linear regression case. This is very often used, is injecting additional terms into the loss function. Okay, and what do these terms look like? So very frequent. So just that you know this, because you will read this probably in the literature. So we talk about the lasso, the ridge, and the elastic net. Okay. These are all kind of similar terms that you can inject into the loss function. And so let's look at our modified loss function. So the loss function that I've just shown you before is just this part here. So we have still our model, we have the features here, we have the target values here, and we have of course the model parameters here. I denoted them J here, omega j, just to point out that it's not just one model parameter, but this can be a vector of model parameters. Okay, so fine, so good. So what you can add here basically is you can basically say, okay, I add to these here two terms. If you add both terms, this is called the elastic net. If you add just this term, this is called the lasso, and this term here is called the ridge term. Okay, what does this mean? So this lambda 1 basically here is we have this omega j here, and basically what we do here, this here denotes basically the absolute values of these omega. So this is basically, if you imagine omega j as a vector, this is the sum of all the absolute values of this omega j. Okay. Why do you do this? Okay, if you do this, basically it will reduce the number of parameters. So it will, in order for the loss function to converge, if this lambda 1 here is basically large, let's say it like this, then it will select very few omegas. Okay, so many of them will get 0 and others they will stay, and that's it. Okay, why this has to do a bit with this diagram, but let's first go into the ridge term. The ridge term might be a bit easier. So what you do here basically is this 2 bars here denotes kind of the L2 norm. This 1 bar denotes kind of the L1 norm. So as I said, the L1 norm is very easy to understand. It's just you take the absolute values of all your model parameters, you sum them up and multiply them by lambda 1. Okay. Here, in this case, basically we take each component of this omega vector squared and take the root out of it, and then basically put this lambda 2 and multiply the result by lambda 2 and also sum them up. Yeah. So basically we have omega 0 to omega j or omega n squared, let's say it like this. If we have this huge sum, we take the root out of all of the sum of these values, we multiply the whole stuff by lambda 2, and we have the ridge term. Okay, so fine, so good. Okay, L2 norm of the vector. Okay. When we look at this diagram here gives us 4 different L norms, as they are called. So as I said, here it's just absolute values that we sum up. Here we sum up all the values squared, and then at the end we take the root out of it. If you look at the absolute values, so basically if you would use this as a distance measure, yeah, this you can imagine that this here is close to the Euclidean norm. Okay, so in 2 dimensions. So if you have just omega 0 and omega 1, and then you could draw a diagram like this, okay? And basically you can say, okay, well, objects that are of the same magnitude, so that here basically under these bars you get the same output, they lie on a line like this, okay? So in this case here, for the first part here on this diamond shape, if you want to, and for the second one, as this is kind of related to the Euclidean norm, we rely on this curved shape, okay? And the story is like, if I want to minimize this, basically this diamond shape, it looks for solution which basically hit the edge of the diamond, and this is basically why many of these will get just set close to zero, if you want to, and some will stay, okay, because these are the ones that hit basically this diamond. And here basically I have a sphere, and so it can kind of touch all of them, but the story is that of course in this sphere term, what this does basically, as it says it down here, it keeps the parameter small, okay, because the more the bigger parameters I have, the bigger my loss function is. It's as easy as that, yeah. Here basically it selects only those that really have some kind of importance, if you want to, yeah. Of course you have to make sure what you set lambda 1 and what you set lambda 2, this is up to your choice. But these are things that you can gear. So why do you want this? For instance, why do you want to have a ridge term? Imagine we have some kind of model where one of these omega parameters basically during the training phase cancel each other out, okay? So if they cancel each other out, what could happen? That both of them explode, okay? So because let's say I have omega 0 plus omega 1, if this omega 0 goes to highly negative, the omega 1 will go highly positive, and I will get very large values. In order to avoid this, I can just use a ridge term, and as the ridge term, basically the larger my values get, the larger the more they will play an influence in here. With this, I can avoid this kind of problem of this, let's say, explosion of parameters, okay? With the lasso term, as it reduces the number of parameters because it kind of selects only those that have really an influence into the model from the small parameters, okay? All of these, basically, if you put this too strong, you get too few parameters. If you put this too strong, maybe your parameters are too small and you never get the right model out. So you have to play with this. Yeah, these are basically hyperparameters, let's say it like this, in the model, this lambda 1 and lambda 2, if you use the elastic net, okay? You can only decide, for instance, just to use the lasso, then you choose just this term. If you just use the ridge, then you use the lambda 2 term, okay? But these values basically help you to regularize your model and to help you basically in the training phase. How do I adapt my omegas in order to fit, in order to get to a correct y, and how do I find basically these omegas correct, okay? This is basically the story about that, what you should know about the lasso, the ridge, and the elastic net for this course, okay? As I said, well, the values for lambda 1 and lambda 2, something that you can do is basically you can, just as we have shown it in the other cases, just use model selection mechanisms like cross-validation in order to get the best lambda 1 and lambda 2 values out for your model, okay? And of course, it can be a goal to build models with few parameters. Then you would like to have this term here, so few omegas, or with small omegas, then you would like to have this term in here, okay? So fine, so good. How do I evaluate a regression model? Yeah, as we say, I mean, with these classification models, it's very easy because either it goes into the right box or not, and then you can calculate the score. Well, how often did I hit the right box and how often did I went into the wrong box? Okay. With these regression stories, it's a bit more complicated, of course. But one of the scores that I want you to know is basically the R2 score. Okay, so the R2 score, what does the R2 score do? basically you just take basically, if you have your data points, of course this can here be hyperdimensional, this doesn't have to be just two-dimensional, then this would look like a bit different, but basically I take the mean of these values, okay, and then I get here the line, okay, this is just the mean value of all the points that I have, okay, and this can of course be here, let's say a surface or a hypersurface, okay, a hyperplane in space in a higher dimensional problem, okay, and you still can basically take the mean of one of these values and build this hyperplane in space, okay, of your prediction value. But the story is basically you take these squares here, so you take the distance from this mean to the point, and you calculate the square here shown as a square, to make this a bit more illustrative, but basically you just take the square distance from this mean to the point, okay. And then what you do basically is then you generate your fit. Of course the fit, nobody tells here that this here is linear, so this could be a curve. Maybe I better would have drawn a curve, but just stay with this example here that I have copied from Wikipedia. But basically this here, you have here basically, you can have here a curve, which is basically a fit. As I said, again, this can be some plane or hyper surface in some space, embedded in some space, if this is a higher dimensional problem. And then you get basically, then you calculate these squares, so the sum of the distances between this fit here and the actual data points that you used to produce this fit, for instance, okay. And what we then see is that we have basically with our surface, so if the fit was good, then this S, so this sum here of all these squares here, so this is just the distance here squared, okay, not to be confused by the square, just the distance basically squared, okay. The sum of these squares should be, of course, way lower than the sum of these squares, okay, if the fit is good. So what will happen then, this will go to 0, and this will here stay at 1. So in the perfect case, of course, this would be 1. The perfect case is not attainable, you can imagine. But you want to have at least some kind of positive number. So sometimes it can happen that this fit is, if I, for instance, would draw this like this in here, okay, then the squares would get even bigger than they are here in this figure. Just imagine this, So if the distance is further away than just from the mean, squared, then this can get negative even, okay. So this is it about the R2 score, and basically you can calculate the score, and using this score you can kind of evaluate your fit, if your fit is good or not. Of course you can just use as an evaluation the loss function that you have used, or some other case. Several times you will read about this R2 score, and I want you to be knowledgeable about what this is and how this looks like. You could use, of course, just the error function that you use, whatever, just to have you knowledgeable about this. Well, the R2 score, for instance, we will then later in the practical see that, as I said, the R2 score can have negative values. And of course, the R2 score can be used, for instance, in combination with cross-validation. So we use cross-validation just as we did it in the classification case, and we can use the R2 score basically to evaluate our models and basically find which model shows the best R2 score. Something like this during the cross-validation on the test set, something like this. Okay, this is basically how it works. So just to go back, how isn't the model, how to evaluate such a regression model. So it's very close to what I've shown you already. This is supervised learning, so it's very similar to the other one. So we have in general a training and test set split. This is of course good, but as you already know, cross-validation is better. And of course further methods might exist. Training test set split, we already have talked about it. It depends on what you're doing. There's no general rule. This size of a training set is good, this size of a test set is good. Especially when you want to predict, for instance, rare events, make sure that in your data set these rare events are frequent enough so that you can train on them. Things on this. So really there is no guarantee a 50-50 split that this is the best. There's no guarantee that a 75-25% split is good. Really make the training test set split according to your knowledge. Think about it, what you want to have, what is a good idea to do, and train and test accordingly. As said, we can use cross-validation, so basically we train on this part, we calculate our model on this part, we predict targets for this part, and then we can use, for instance, the R2 score, how well we predicted these targets. Okay? As easy as that, we can do this several times, and we can then calculate mean deviation from these R2 scores and see, well, which we can do this even for different models and can evaluate basically a model's performance. So we do this, for instance, 10 times. We do our training test set split. We have 10 folds, also this is called in the literature, and we see basically, okay, for this we get this R1 score out, for this split we get another R1 score out, and then we can basically make statistics about the R1 scores that we got out. And this is of course better than just doing one training and test set split. It also hopefully covers the whole data set in some kind of ways. Okay, so far so good. This is everything that I wanted to show for the regression story. I hope you liked it, and we will see each other soon again for the practical. Bye bye.